All right, welcome back. So in this video, I would like to discuss a few metrics that are used to evaluate a photodetector. So this will not be exhaustive. This is the first level. So we'll just introduce some of the responsivity, which is one of the most important metric, and then we will just mention the other things. All right. So of course, there are a whole lot of things that are required for practical device design. All right. The first thing we'll talk about is responsivity. So this is a very important metric because it quantifies how many electrons are produced when you have a certain amount of, how much current is produced by detector per unit power, right? Your essentially your input is optical power, which is, let's say, P, power, incident power, like let me call it as incident power, 1 milliwatt, 1 microwatt, whatever, right? Incident power. How much is the current that is produced? We would like to estimate that, and that can be captured by what is known as responsivity. So I'll say current, photocurrent, right, is going to be equal to what? Well, if you have an incident power, that is going to have some definite flux of photons, right? How many photons are there per second? We can compute that. We have done it in the past. So that I'll call it as phi, which is basically flux of photons. And then not all of them will produce electrons. Okay. So to capture that, we will introduce a parameter which we call as quantum efficiency. Sorry, eta. Okay. I'll just talk about it in a moment. And then, of course, the charge. Okay. So what are these parameters? Well, phi is the flux of photons, right? Flux density, you could call it. Okay. How much is it? This is going to be, if you have, let's say, power of P, we have seen that the number of photons that are produced per second per centimeter square is going to be h nu, right? This is the energy of the photon. Of course, you have to put a Q there because if it's in EV, of course, you have to put a Q. Otherwise, P by h nu will be the flux, the number of photons that are produced per second. All right. So eta is the quantum efficiency. Essentially, how many photons, how many electrons is it producing per photon, right? And ideal detector, this is going to be eta equal to 1. Okay. If it's not ideal, we'll see that it's never going to be ideal. It's going to be slightly lower quantum efficiency, but we would like it to be as close to 1 as possible. And the last one is charge. So you can actually, rewrite this. So this will be QP by h nu, right? And so the current versus power, right? The responsivity we are defining as the amount of current that is produced per watt, right? So the way we are defining is it's in the ampere per watt. Okay. So that can be captured by this expression here. This term is called as responsivity. Okay. So what is this? Well, rather, I forgot eta. Right. So this is going to be eta and then h nu by q. Well, h nu is energy of the photon divided by q is basically energy of the photon in the EV units. So this will be equal to eta by energy in EV, right? EV times power. Our responsivity is going to be simply eta by this one. And we know that this guy is going to be equal to 1.24 divided by lambda in micrometers, right? So responsivity now, R is going to be equal to eta by 1.24 times lambda in micrometers. Okay, this is the responsivity for an ideal photodetector. Okay, so if you have lambda equal to 1.24 microns, this is lambda in micrometers. Okay, that is this is lambda in micrometers. So if your lambda is 1.24, responsivity is going to be 1. And that is what is shown on the graph here. So as you have ideal photodetector, responsivity should go up to 1.24. Okay. If your lambda is larger, of course, it will show something. Okay. But what happens is, if you're above the band gap, you're not going to get any responsivity. That's why it quickly drops here. Okay. And then for the lower wavelengths, you're going to have smaller current, that is smaller responsivity. Okay. But this is the ideal case. If you have a realistic case, the responsivity is going to be something like this. So if your photon is actually having longer wavelength, that means the energy is less than the band gap and it cannot produce any electron hole pairs. So on the longer wavelength, it has to drop. Okay. On the shorter wavelength, I mean, if your energy is very, very large, per watt of photon, for per watt of optical energy, you'll have lesser number of photons, so lesser number of electrons. Okay. So here, lesser photons per watt, right? Because power is, whatever, unit power, right? And as you go to lower and lower wavelengths, the energy of the photon is larger. So the number of photons per watt is going to be less. And that's why the responsivity drops. Because we are essentially capturing responsivity in terms of number of electrons per watt. Okay. So, I mean, indirectly, it is going to be proportional to the number of photons. Okay. So on the higher wavelength side, this is basically drop because energy is, h nu is less than Eg, so responsivity is 0 there. So this is the typical curve you'll see. Well, this is for silicon. It turns out that you can have various materials because in the beginning of the photodetector discussion, I said that we would like to have detectors in various wavelength ranges. Okay. For silicon, you can go up to 1.1 microns in the longer wavelength range, but you can't do better than that. So if you want to have a longer wavelength detection, we need to use, for example, germanium. Germanium has a band gap of 0.8 eV. That means it can detect up to 1.5 microns or so. So that's why you see that the curve here, this is basically germanium, which is having a photo detection of up to 1.5 microns, and you have slightly better responsivity. And silicon has this responsivity, and various materials. You see that there are a couple of other materials here. We will talk about it in the next week. These are basically 3,5 materials. Okay, other 3,5 materials, we'll talk about it. So gallium arsenide, indium arsenide, and so on. Okay. So you might be wondering, definitely some of you must be wondering that we said that silicon and germanium, they're indirect band gap materials, and they're not very efficient in interacting with light. Then how are we using them as photodetectors, right? It sounds counterintuitive, but it's not. The reason is, for photo detection purposes, what we care is, how many electrons are we able to collect. And one of the key parameters that influences that is a minority carrier lifetime. We have already seen that, tau p, right? Tau p or tau n, minority carrier lifetime plays a crucial role, right? Minority carrier, sorry, what is this? Minority carrier lifetime plays a crucial role for detection, photo detection process. Okay, what is that? Well, you're generating electron hole pairs and you don't want them to recombine. Okay, so since we said that indirect band gap semiconductors are not good at interacting, interaction of photons and electrons is not very efficient there. So indirect band gap semiconductors, indirect band gap materials, tau is large relatively. Tau is smaller for direct band gap materials. That means if you generate, it's very efficient to generate electron hole pairs, but it's also efficient to recombine them. That's why tau is smaller for direct band gap semiconductors. Whereas indirect band gap semiconductors, it can go up to even 10 power minus 6 microseconds scale. Okay, tau is large, and because tau is large, we can build a device in such a way that before it recombines, we try to collect the electron. Okay, tau is essentially capturing how much time is there before electron is recaptured, electron and hole recombine, right? Effectively. So before that recombination happens, we try to collect them in the external circuit, and that is why, even though silicon and germanium are not really that efficient materials for interacting with light, we just increase the width of the material so that we collect more photons. Okay. Per unit length, definitely direct band gap materials will absorb many more photons, but we can overcome that by increasing the width of the material and then collecting the electron hole pairs. So that is why silicon, even silicon solar cells, I started the discussion by saying that silicon is not a good material for optoelectronic applications, but then I showed you silicon for solar cell. Well, the same reason, silicon also you can collect these electron hole pairs efficiently. That's why silicon solar cell behaves reasonably well. I mean, if you build a gallium arsenide based solar cell, that's even better. Of course, we do that. It has much better efficiencies, but it's expensive. Okay, so for silicon it's cheap, so we try to use silicon solar cells. Similarly, you can make photodetectors out of silicon and germanium, and they still work. All right. So responsivity is one of the metrics that is very important. And you saw that the responsivity of various detectors can be changed because each material has a different band gap, and based on that you can have different amounts of responsivity. I mean, we can use PN junctions. We can also use Schottky junctions. For example, here what is shown is the Schottky junction. In this case, silver and zinc sulfide junction can have responsivity even in the very small wavelength range. And gold and indium gallium arsenide can have responsivity in the larger wavelength range. So these are basically Schottky junctions. These dashed curves, dashed is Schottky junction. Even there you have a depletion region. So because of that, you can use it for photo detection purposes, and they have some advantages. Okay. So there are a whole lot of materials that are available for us to choose from. And how do we choose which photo detector to use? Well, it depends on a few parameters. This is just a small short summary. It's by no means exhaustive. There are many more parameters that need to be considered. But for the purposes of an introductory course, I thought I'll just mention these. So the images that you see on this slide are some images of practical photodetectors that I've taken from the website Thorlabs. Thorlabs is one of the suppliers of these things, prominent suppliers of various optoelectronic components and optomechanical components. So here what you're seeing is basically a APD of certain specifications. The specifications are written on the detector itself. And this is again a photodiode, a simple photodiode. I showed you the schematic in the previous video. So this is how practically it will look like. There are some leads that are coming out. You connect it to external circuit and you shine light on this guy here in the window, and it will collect, it will generate current. That's it. It's quite small. It looks like a BJT or something, in the previous, if you used them in the labs. Well, I mean, this is just two detectors. There are a lot more detectors. How do we choose from that? Okay. So mainly, there are three technical considerations that are important to us. One of them is the spectral range. Okay. So we cannot use every detector in every spectral range. For example, silicon, I can go from visible to near infrared. I can't really do better than that. So this is going to be having better responsivity in this range. Whereas germanium is going to have better responsivity in the near infrared. Near infrared is 1.5 micrometer. And this is a very important material, a very important spectral range for technology. Because if you have optical fibers, all of them are actually communicating at 1.5 micrometer, 1.55 micrometer wavelength. Okay, all the fibers, everything, right? You have internet in your home. The fiber is actually having 1.55 microns. And how are you connecting the optical signal into the electrical signal which is coming into a computer? Well, you need a photodetector there, right? And gallium phosphide in the UV you can reach. Similarly, you have some other materials which are, indium aluminum antimonide and things like that, which can work even into the mid infrared. For example, you want to detect, temperature of a furnace, high temperature furnace, right? 1500 Kelvin. You need some detector in the mid infrared range. If you want to detect human bodies, thermal imaging of human bodies, for example, nowadays we have the pandemic. So if you go into an airport, they might want to screen you, for temperature, but they can't, screen everybody for temperature, right? With a thermometer. So what they do is they have these thermal images installed. So when you have a person just going in front of it, if the person has a temperature, the thermal imager will show you that, will flag the person, then they'll stop him and then ask him a few questions. So that's how you can quickly screen. For example, in airports, railway stations, you can have thermal imagers, which will work in the long wavelength IR. I'm not even discussing those things here. And those are pretty expensive actually. Okay. So the spectral range over which the detector operates is an important parameter. Another important parameter is how fast it can operate. Okay. Some of them are high speed. For example, silicon or, this 3-5 semiconductors, this can be high speed sometimes. And one of the parameters that influences the speed is the area of the photodetector. Area small implies high speed. Okay, so that means your collection area, for example, this guy here, I mean, if you go to Thorlak's website and search for photodetectors, you'll see a whole collection of detectors, and you can analyze. You'll start seeing that this area that is there, right, active area, if it is small, then the photodetector's speed will be larger. Okay. So, and also, of course, the mobility of the carriers and all play a role. So there are various options that are available here. You can choose, it's just, quantified as high speed, low speed. But in principle, what you look for is the rise time and the fall time. Rise time, fall time. Okay. If your detector has nanoseconds of rise time, okay, it's normal. It's going to be cheap. But if you want a detector with picoseconds of rise time, okay, that's going to be much more expensive. The reason is, let's say in a communication, you don't want to operate at megahertz. You want to operate at gigahertz, hundreds of gigahertz, right? As fast as possible, you want to switch them. You want to switch, 0 and 1, switch on light, switch off light, and measure that, pulsing. For that, you need a very high speed detector. For that, you would want, picoseconds, hundreds of picoseconds at least. Okay. So if you want high speed, then it's going to be expensive. Okay. Of course, yeah, that's what one of the parameters is cost, which, I just, how much is moderate, how much is low, how much is high, it depends. When I was a student, I would say that even $100 is expensive. Nowadays, $10,000 is expensive. So, I mean, it depends on, what you're exposed to. Okay. And the last parameter is dark current. I've already alluded to that in the previous discussions. So if you have a large band gap, you're going to have smaller dark current, right? That's why gallium phosphide, for example, has 2 eV band gap, and so it has a low dark current. Okay. But if you go to MCT and these things, indium antimonide, indium arsenic antimonide, they have low band gaps. They can have high dark current. So what happens if you have high dark current? Well, large dark current implies low SNR, right? So, yeah. And what is the amount of, limits of detectivity? How small can you detect and things like that in terms of noise equivalent power, if you increase your optical power, it's going to have more noise. So there's something called as noise equivalent power. You can calculate a whole range of parameters, and you can choose which detectors to use based on those parameters. All right. So I hope I have given you a glimpse of photodetectors with these lectures. So I'll stop my discussion here. So far in this week, we have discussed photodetectors, essentially devices that can conduct photodetectors and solar cells, right? Essentially devices which are converting light to electricity. So this is one class of optoelectronic devices. In the next week, I want to talk about the opposite process. I want to generate photons from electricity. Okay, so those are devices like LEDs, lasers, and so on, and even displays, CCD displays. Charge shockable display will actually measure. Well, you have displays also which are going to emit light. So, yeah, we want to discuss light emitting devices in the next week of the course. And with that, I will close the discussion of this semiconductor devices. All right. So take your time, go back and look at the videos, and if something is unclear, we will have a discussion one-to-one. We will have certain time slot that will be announced. So you're welcome to approach me and we can discuss it further. All right. So thank you very much. I'll see you next week. Bye.